Hello everyone. Welcome to a brand new section, Protocols, Abstract Data Types. An abstract data type, ADT, is a description of what a data structure should do for its user. It is a list of operations that any implementation must support and the complete description of what these operations are supposed to do. In this section, you will learn about the definition of some common ADTs and their operations, and how to implement these ADTs using both simple arrays and data structures you learned in the last section. So let's get started with the first video of the section, Stack. In this video, we will learn about stack and its operations. We will create a fixed-size stack using array and a variable-sized stack using linked list. A stack is a very commonly used ADT. It is so named because it resembles a stack of plates used in a restaurant. In such a stack, a plate that has been washed and put last would stay on top. This would be the first plate to be picked up when a plate is needed. The plate that went in first would be at the bottom of the stack and would be picked last. So the last plate to be placed in the stack is the first plate to get out. We can also call this last in, first out, LIFO. Similarly, a stack ADT has a protocol where the last value that is put in it must be returned on the first attempt to get a value out, and the value that went in first must come out last. The operation of putting a new value in a stack is called push, and the operation of retrieving a value from a stack is called pop. The element that was pushed last must be popped first. The operation that allows one to see what the next pop will return is called peek. The peek operation returns the top element without modifying the stack. We expect all stack implementations to have all operations implemented in the time complexity of O of 1. This is also part of our stack protocol. Since we know that ADTs are to data structures what interfaces are to classes, we will code an ADT as an interface. So, I am creating an interface for stack. Stack interface will have three methods: push, pop, and peek. Push adds an element at the top of the stack. Pop removes the element at the top of the stack. Peek checks the next value to be popped. Of course, we will not leave it at this. We will see how a stack can actually be implemented. To this end, we will see both a fixed-sized stack using an array to store its data and a growing stack using a linked list for storing data. We will start with the first. Now let's look at fixed-size stack using an array. A fixed-sized stack uses a pre-allocated array to store values. That is, when the stack has used up the entire array, it can no longer accept new values until the old ones are popped. This is not very different from an actual stack of plates, which most certainly has a maximum height that it can handle. As always, we start with the basic structure of the class. Stack implements array. This class will implement stack interface. Then we will add the required Java libraries. We need an array to store the elements, so we will create an array for our stack. We need to remember where the top of the stack is in that array, so we will create a variable top. The top always marks the index of the element that will be popped next. When there are no more elements to be popped, it is set to -1. Why -1? Because this is the natural choice, as it does not require any special handling when the first element is inserted. Now we will initialize the size of our stack. The push operation in a stack can be to simply put the value in the array right next to the current top, and then set the top to the new position. I will add this code to override the push method. We pass the value to be pushed. We first check whether the stack is already full or the current top is equal to the maximum index possible, like this. If this is the condition, then we throw no space exception. Now we set the top to the new position and put the value we need to store in there. The exception we used is a custom exception for this purpose. We have to create the class for no space exception. This is our no space exception class. This class will extend runtime exception. Now add the constructor for this class. Now override the pop method. The pop operation is just the opposite. We need to first take the value of the current top and then update the top to the new position, which is one less than the current position. Here you can see the code for that. We first check whether the stack is already empty, in which case we return a special value, null. Then we update the top and return the value at the current top. Next, we will override the peek operation. The peek operation does not change the state of the stack and hence is even simpler. This is the peek operation. Just like the pop operation, we will return null if the stack is empty. Otherwise, we return the top element. Now we will implement the main method. This is the complete code. We have created a stack here. Here we have added elements using push, popped the elements, and then peeked at the element. We have again pushed an element and then again printed it. When I run the code, I get this output. So let's see. I get the pushed elements popped first. When we peek now, it gives a null value. Then again, when we push 99 and peek, we get the value as 99. Let's look at variable-sized stack using a linked list. The problem with an array-based implementation is that since arrays are fixed in size, the stacks cannot grow beyond a fixed size. To resolve this, we have to do what we did to fix the same problem for an array, that is, use a linked list instead. We start such an implementation with the stack implements linked list class. We create the class here. Add the Java libraries. The linked list will store the values. Instead of assigning a new linked list to it, we do so using an overridable method, getNewLinkedList. This will be useful in the class that extends from this one. After this, I will create the getNewLinkedList method. This will return a new linked list. To see which end of the linked list must be used as the top of the stack, we need to remember that our stack protocol expects the operations to be O of 1, so we must choose an end that allows both insertion and removal in O of 1 time. That end is of course the front of the list, as we saw in the last chapter. Now we will add the push method in the stack. Here it will append the element at the top of the stack. Note that this time we did not check whether the stack is full because this implementation of the stack is never full. It grows as it needs, and the underlying linked list takes care of that. The pop operation, however, does need to check whether the stack is empty and return null at that point. So here is the pop method. We return null if the list is empty. We return the value of the element removed. The peek operation is of course the same, except it does not remove the top element. Here is the code for peek. We return null if the stack is empty and return value of the first element. This concludes our linked list-based implementation of a stack. Now implement the main method with this code. This is our main method. Here we created a stack using linked list of the type integer. Here we have added elements using push, popped elements, again pushed an element into the stack, and implemented peek. Yes, all our methods are working properly.